In this section, we're going to look at the basics of spectra and how they are produced. Niels Bohr, many years ago, was able to demonstrate that you can think of an atom, it's not a perfect way to think about it, but you can think about it as being like a solar system, like having a sun in the middle and orbits as it moves outward. This is not a correct view, but it's useful, and that's what science does. It gives us useful ways for us to look at the universe, even though they may not be correct. So in his model, the Bohr model of the atom, he said there's a positively charged nucleus at the center of the atom and locations where an electron could orbit around the nucleus. And frequently these are labeled n equals 1, n equals 2, n equals 3. And the lowest one is referred to as the ground state, like the ground outside. That's where the electron tends to go most often, is the ground state. Anything that's not in the ground state is said to be in the excited state. And to get from the ground state to an excited state, the electron must get energy. And that electron can get energy. That electron must get energy that's equal to the energy difference between those two orbits. And that can occur in a couple of different ways. And for our interest, it can occur when light comes in and strikes the electron. And if the energy of that electron is, if the energy of that light is equal to the energy difference in that orbit, that electron will go from one level to the other level. So it'll go from n equals 1 to n equals 3. And this is when the electron takes energy out of light. Now, just like a ball that's tossed in the air, electrons tend not to stay in excited states very long. The ball will go to the top of its flight and come back down to the ground. And so an electron, when it goes from energy electron to 1 to 2, it won't stay there very long, fractions of a second, and then will fall back down to level number 1. And when it falls back down to level number 1, as the diagram describes, it will emit a photon. It will emit energy that's equal to the energy difference between the two orbits. And this energy is demonstrated to us as a color, as a wavelength of light, in particular invisible light, or it could be an ultraviolet, or it could be an infrared. And that is the way that we get energy produced in these atoms, or energy demonstrated in these atoms, and this produces a distinct fingerprint of light. And in particular, when the electron goes from a level number 3 to level number 2, or level number 4 to level number 2, that is where we can get visible light. Anything that is going from down to level number 1, that's usually a higher energy, that's in the ultraviolet. And this picture shows these different energy level, what we get. We get ultraviolet out of the Lyman series. We get Balmer series as visible light. We get infrared and so on in these other, the smaller energies. So it means longer wavelength. So it's possible for us to see this Balmer series of light for hydrogen, and these are distinct colors. These are distinct colors of light that the hydrogen atom emits when the electrons go from the ground state to an excited state and back to the ground state again, primarily when it goes to the ground state, or to level number 2. The ground state is the Lyman series, level number 2 is the Balmer series. And most importantly is that all of these different energy levels are unique to each chemical element. That is the very important part here. Hydrogen has a different energy level from helium, helium from neon, neon from other gases. And so every chemical element has its own fingerprint. And so when we make a spectrum of hydrogen gas, we get this unique fingerprint of light coming for hydrogen, and this is its signature. This tells us that hydrogen is present, and the most famous one transition here is from the n equals 3 to n equals 2. This is what we refer to as the hydrogen alpha line. It's red, clearly distinct in pictures, and very easy to see. This red, and in particular this blue line, those are very easy to locate. These blue colors are very easy to locate. So when you see a visible picture of an object in space, like this one, this is visible light. This is hydrogen alpha, this red, and we're getting some other hydrogen transitions in here too. So this is caused by the sun, these stars, shining on this gas. Normally the gas is clear, like the air around us is clear. Nitrogen, the predominant piece of our atmosphere, component of our atmosphere, is mainly clear. When you look across the room, there's nothing that gets in your way in the air. Hydrogen, helium, nitrogen, oxygen are normally clear when all of their atoms are in the ground state. This is a spectrum, a visible picture in the visible part of the spectrum of this gas cloud. And sometimes you have to be careful these days because many photographs that you see are composites of different wavelengths, such as a composite of the ultraviolet with the infrared, and you have to look very carefully at the picture to see it's a composite because blue does not necessarily mean visible light. It could mean ultraviolet. The red could mean infrared. So you have to look at these composite pictures because they change the colors in them. But this is a natural photograph showing the hydrogen spectrum in these particular gas clouds. And so comparison of a couple of gases. So hydrogen gives us its distinct fingerprint. Mercury has its distinct fingerprint, and neon has its distinct fingerprint. This is what causes the neon lights to glow by getting these electrons excited, and then they fall back down to their ground state. And notice that some of these colors are pretty close together, but it is possible to really measure their precise wavelength and to identify the chemical element because of its preciseness. Notice here between these elements we have some colors that are very close together. Obviously, one color line by itself is not the distinguishing factor, but notice when you couple the pairings together, you see that this is a distinct fingerprint of this particular gas. So the main component here is that every chemical element has its own fingerprint of light that we can identify in the type of spectra that we're about to talk about in this chapter. This is very important for our understanding of what we know about the universe. Because we cannot sample it, we can study the starlight or the light from the galaxy or the light from the nebula, and one of the things that we can tell is its chemical composition, this particular fact. And we can see the example of hydrogen alpha, the hydrogen spectrum in this gas cloud, when the electrons are excited to higher energy levels by the surrounding stars, making that gas glow. And we see it. But normally the gas is clear when it's in the ground state, and we see right through it. In the excited state, we can see the beautiful colors of the universe.